In this section, we want to make sure we understand the exponential equality property. This is really handy. It says that if you can get the same base on each side of the equal sign, then the exponents will be equal. So what we're going to do is we're going to look at these problems and see, is there any way that we can make the bases be the same? So for problem number 1, we can see that we have a base of 3 on both sides. Since the bases are already the same, all we need to do is set the exponents equal to each other. And now we can solve. So I'm going to add x to both sides. And I'm going to subtract 5 from both sides. And then I'll divide both sides by 3. And I'll get x is equal to 2/3. And we can put this back in and check it. Our next problem, though, is not so straightforward because we don't have the same bases on both sides. But 49 we know we can write as a base 7. 7 squared is 49. So I can replace 49 with 7 squared. Now we know that when we have a product raised to a power, we simply multiply. So we're going to distribute that 2 to just as if it were multiplying 2 on the outside times 2x plus 3. Now, our 7 on the right does not have an exponent. When we don't have an exponent, we know it's really a 1. So this will become 4x plus 6 is equal to 1, which I can solve because it's a simple linear equation. And I'll get x is equal to negative 5/4. Problem number 7. Now, this time we can see that our base for our exponent here is going to be 3 on the right, and on the left. And on the right is 27. We want to have the base be the same. So I'm not going to worry about the 9 right now. I'm just going to worry about the base. So I have 3, and then it's raised to the 6x minus 1. And I'm going to rewrite 27 as 3 cubed. 3 cubed is 27. So I could rewrite this, and I know I have a 9 out here too. So I could rewrite this as 3 to the 6 minus 3x. And over here I have 3 to the 6x minus 1. Okay, so now that we have the bases the same, let's look at this number in the front, 9. Could we rewrite that as a base 3? We could. 3 squared. Now, let's think about our properties of exponents. When I have like bases, I add the exponents. So I could rewrite this as 3 raised to the 2 plus 6x minus 1. Well, super. Now we can just equate the two exponents. So I'll have 6x plus 1 is equal to 6 minus 3x. So I'll add 3x to both sides, and I'll subtract 1, and I'll get, and then divide by 9, and I'll get x is equal to 5/9. Okay, let's move on to our next problem. We'll try number 8. So this one here I can see is a base 5. So I want to make 125 with a base 5. So that's the same as saying 5 to the 3rd power. So I'll equate the exponents. Now this is a quadratic, and we know with quadratics, we want to have them equal to 0. So we can maybe try using the factor property or the quadratic formula. I'm going to try the factor property because I believe you can factor here. And I'm going to get x plus 3 is equal to 0, and x minus 1 is equal to 0. So x is equal to negative 3, and x is equal to 1. And then number 9, we're going to say 2 to the x squared plus 3x. And we're going to rewrite 16 with the base 2. That's going to be 2 to the 4th power. So we're going to have x squared plus 3x is equal to 4. The quadratic, so once again, we're going to look at it and see whether it's possible to factor it. And it is. So we're going to get x is equal to -4 and x is equal to 1. So solving using the exponential equality problem is the best one because it's usually the most straightforward one. Okay? But unfortunately, we don't always have that. So we're going to try some different methods in this section. 13 asks us to solve the exponential equation. It asks us to first give the answer in logarithmic form and then, okay? So first what I want to do is I want to get this exponential expression on one side. So I'm going to add 2 to both sides. And I'm going to get 57.6 is equal to 1.2 e to the -4.1x. Okay? And now I'm going to divide both sides by 1.2. Once again, just trying to get that e to by itself. I'm going to leave it just like that for now. Now, I'm going to rewrite this as a logarithm. So we know a log is another name for an exponent. So my base is e, because that's my base over here. My exponent is -4.1x. And then I'll put my 57.6 divided by 1.2 in here. Now we know log base e is another way to say natural log. And then to get x by itself, we'll just divide both sides by -4.1. So let's put that on our calculator and see what it looks like. Enter it in my calculator, and you can see I made sure to put parentheses around this 57.6 divided by 1.2, and then I divided by -4.1. Hit enter, and I'll get -0.944. Let's try the next one. So once again, I'm going to add 1 to both sides. And then I'm going to divide both sides by 30.4. I'm just trying to get that term with the base and the exponential term by itself. And then I'm going to add 1.6 to both sides. So that will give me 10 to the -7.9x is equal to 14 over 30.4 plus 1.6. Okay? Now let's rewrite this as a log. So it's going to be log base 10. And then my exponent is going to be the other side. A log is another name for an exponent. So it's 14 over 30.4 plus 1.6. And I just leave them like that. I don't reduce them or simplify them because it just makes it more accurate. And then a log is another name for an exponent, so put the exponent on the other side. So I'm going to divide both sides by -7.9, get the x alone. Let's put that on our calculator. I've entered it in, I hit enter, and I get 0.0397. So in our case, we're going to round up to 0.040. If you're using this method of just rewriting it as a logarithm, you have to remember that you have to be careful and you have to put it into the calculator very carefully. Your goal, though, is to make sure that you get the exponent with the base alone. So you want your exponential expression alone before you attempt to rewrite it. Let's try the next one. I'm going to use the same method. I'm going to add 3 to both sides. And I'm going to get 7 to the x is equal to 6. Now all I need to do is rewrite this as a logarithm. So it's going to be log base 7 of 6 is equal to x. That wasn't hard at all. The only tricky part on this is you have to understand now, though, that you can't put a log of base 7 into your calculator. So if you're going to use this method, you're going to need to change the base. And the change of base formula tells you to change your base by rewriting it. So log of base 7 to the 6th, what I do is I put my base on my bottom, and that way I remember base and bottom. And then you can change it to whatever base you want, but we're going to do base 10 because it's usually the easiest. So now if I put log of 6 over log of 7, this is going to be now changing it to log of base 10. Okay? So if I enter this in my calculator, I'll say log of 6 divided by, let me put this in parentheses, log of 7, and I get 0.921. But this is not the only way you could do this problem. So let me show you the second way that they show you in the PowerPoint. The second way is you use those the properties of the log. And first I do the same thing. I have to isolate my exponential expression. But when I get to this step, instead of doing what I did a minute ago, instead I'm going to rewrite it by taking the log of both sides. So as long as I do it to one side and do it to the other side, I haven't changed it. So right now I have log of 7 to the x is equal to log of 6. And we know that the exponent properties tell us that if you have a log of a number raised to an exponent, we can put that in the front. So this becomes x log of 7 is equal to log of 6. And you can see now that we can divide both sides by log of 7, and I'll get the same number, log of 7 over log of 6, which turns out to be the exact same number that we got earlier when we worked it. It's just a different way to do it, and that's just using the logarithm properties. Try the next one. So I'm going to rewrite this as a log. So I'm going to say the log of base 6 and an exponent. Log is equal to an exponent, so put it on that side. Okay, so that looks great. Unfortunately, my calculator doesn't have a log base 6, but I can easily change it. The way I do it is I divide by that base. That'll give me a log of base 10 of 1.9. And then I'll divide both sides by a negative 1/2. Now I can use my calculator, so I'm going to say log of 1.9 divided by log of 6, and then I'm going to multiply times a negative 1/2, which is 0.5. And I get negative 0.179 for my answer as an approximation. Now to do the alternative method, I just take the log of both sides. Okay, and we'll bring this exponent in the front. So I'm going to divide both sides by negative 2 log of 6. And I'll end up getting the exact same thing I did a minute ago. I'll get the same value, just a different way to get there. I'm just going to show you that because they're going to introduce that throughout this section in the PowerPoint and the book. And you can use either method you like. Let's do problem number 19. So I'm going to try to get my exponential by itself. So I'm going to subtract 1. And then I'm going to divide by 4, still trying to get that exponential alone. Now, when you get to this point, it's really up to you. You want to use the logarithm properties, or do you want to use the rewriting it as a log and changing the base? Your choice. I think for fun, I'm going to go ahead and take the log of both sides. So I take the log of this side, and I take the log of this side. When I take the log of a number, if it has an exponent, the exponent can come to the front. I'm going to get 2x minus 3 times log of 6. Notice I put it in parentheses since it's an expression. Is equal to log of 4. Now I want to divide both sides by log of 6. And I'll get 2x minus 3 is equal to log 4 over log 6. So I'm going to add 3 to both sides. That will get rid of the 3. And now I'm going to divide both sides by 2. And that will be x is equal to. So x is equal to, and I can put this in my calculator. I'm going to say log of 4 divided by log of 6. And then plus 3. I'm going to enter, and then I'm going to divide by 2. And I'm going to get 1.88, take a peek at that again, 7. Remember, these are approximations. The other method, let me get you going on that. So for this method, you would rewrite it as log base 6, right? And it's going to equal the exponent. So if we wanted to put this in our calculator, we'd have to put it as log of 4 of log of 6. Base goes in the bottom. And then we'll do it the exact same way. We'd add 3 and divide by 2. And you'll get the same number. Different method. It's okay. You can choose which method you like on the test. Okay, now on this section, they want to review the properties of those logarithms. So I went ahead and sneak over here and so you can refer to them as we're talking. So first of all, we want to make sure we understand the product property. It means multiplying. So when you have a log of m plus a log of n, you could rewrite it as log of mn. Okay. Now be careful. Log of m times log of m, n, does not equal log of mn. It's very deceiving. So log of mn means you have to add the two logarithms. Next one is the quotient property. Similar. It's a tricky one. Log of m divided by n does not mean log of m over log of n. It does not work that way. It means log of m minus log of n, if you wanted to expand it out. Okay? And last but not least, the one we already kind of talked about a bit, and hopefully you saw in the PowerPoint, is that when you have a logarithm and it has an exponent, then you can take the exponent and put it in the front. Okay, the logarithm of kth power of m is equal to the exponent k times the logarithm. And these properties also apply to the natural logs too. So let's look at these. So problem number 29, you can see it's addition. So I can rewrite this as log of 8x. And I just multiplied the 8 and x. The next one is subtraction. So I can use my quotient property and say x minus 2 over x squared minus 4. And I know that I can simplify this because I recognize that as a difference of squares. So I'll end up with the natural log of 1 over x plus 2. Keep going practicing those, okay? And we're going to use them now this time to solve. Now, I'm showing you how to do it because it tells me to use the properties of the logarithm, but you could use the rewrite the base method and then change the base. It would be either way, it'd be fine. So if I'm going to use the properties of logarithm, then first I'm going to divide both sides by 12. And I'm going to get log 4 of x is equal to 5. Okay. We can convert this to exponential form and say our base is 4, our exponent is 5, and it's equal to x. 4 raised to the 5th power is 1,024. All right, let's look at problem number 53. So here we go. We know that this is a quotient problem because it has subtraction. So it's log base 3, and they're both the same base. I'm going to say 5x plus 1 over x. So let's rewrite this as an exponential. So it's going to be base 3, exponent 2 is equal to 5x plus 1 over x. This will be 9. If I multiply both sides by x, then this will become 9x is equal to 5x plus 1. And if I subtract 5x from both sides, I'll have 4x is equal to 1. Dividing by 4, I'll get x is equal to 1/4. Okay, so now let's do number 59. First, I'm going to isolate the log by subtracting 7, so I'll be -9, and then dividing by -3. So I'll have the natural log of 5x is equal to 3. Okay, and I can rewrite this as base e raised to the cube is equal to 5x. And I'll divide both sides by 5. Use my calculator. So I'll say second natural log cubed, enter, divided by 5, and I get 4.017. I just noticed it says 4. I had only done 3, so be careful on yours and do the correct decimal places. Okay. We have 2 more problems, so let's do number 49. So we want, once again, to isolate the log. So we're going to subtract 4 from both sides. Rewrite this base 2 raised cubed is equal to 4x minus 1. 2 cubed is 8. I'm going to add 1 to both sides and divide by 4. So x is equal to 9/4. One more problem. Let's talk about number 55. You can see that there's addition between the two logarithms. So that's going to indicate the product rule. Same base, so it's going to be log of 4, and it's going to be x plus 8 times x plus 2 is equal to 2. So I can write that as the log of base 4 of x squared plus, if I distribute this out, it'll be 10x plus 16 is equal to 2. If I use my knowledge of logarithms, I can say 4 squared is equal to x squared plus 10x plus 16. It's a quadratic, so I want it to be equal to 0. So I'm going to subtract 16 from both sides, and I'll get x squared plus 10x is equal to 0 when I subtract 16 from both sides. Now, it's a quadratic. I'm going to factor out an x, and I'm going to get x plus 10 times x. So I know that x is equal to 0, or x is equal to -10. Now, the last step I should have mentioned on all of these is to remind you, when you're doing a log and you're solving, you always have to check to make sure you haven't created extraneous solutions, which means that you always want to take the log of a positive value, never a negative value. So if I put in a -10 for x back into my problem, I'd see that I would get -10 minus 8 would give me -2. And -10 plus 2 would give me -8. So therefore, I'm going to get rid of that one, and I will only use x is equal to 0 because it's the only one that doesn't it's the only one in our domain. So be sure on these to check your solutions. It's not a matter of being goody two-shoes. It's a matter of sometimes you're going to find that you've created a solution that's not in the domain.